Okay, so it is my pleasure to introduce Professor Joydeep Dutta. He works on all kinds of different optimization kinds of areas. I see him pop up in things that I'm looking at all the time. I know he worked with John Borwein on things related to Fitzpatrick functions, and I know he's worked with Regina Burachik on things related to proximal point methods. And so those are both really interesting things to me. So I'm certainly excited for his talk on a simple algorithm for the simple bilevel programming SBP problem. And please join me in welcoming Joydeep Dutta.
Thank you very much, Paul. And I see I have a lot of friends here, and I see Nadia, Julian. Good afternoon. And of course, I see Regina, who has to take the blame of getting me interested in algorithms in the first place. So, in case Regina, you are there, hello.
Hello, Joydeep. Hello.
Hello.
Nice to see you.
You see, I have still interest in algorithms. See, the problem here is actually a very simple one. There's a convex. You are solving a convex optimization problem, and then you want to minimize another convex function over the solution set of the optimization problem that you have solved. This is very practical because, for example, if you solve a linear programming problem and you want a least square solution, so basically then you are taking the solution set of the optimization problem, the linear programming problem, and then you want to minimize, say, half of norm x square over that solution set. But the idea of this whole story is how not to actually solve the first problem and rather completely solve the thing that you want without really going and really solving the first problem. So this is a generalization of the so-called bilevel programming, which is pretty popular nowadays. But this problem has some very interesting applications. So we will first introduce the simple bilevel programming, which is what I have just told. See, one of the things which has driven us to do this is most of this algorithm that is there in the literature. See, my first interest in this particular problem came from a 2000 paper by Mikhail Solodov in Journal of Convex Analysis. Actually, I was reviewing the paper for math reviews, and then I saw it. It was very interesting. So what is very interesting is that in these kind of algorithms for these particular type of problems, so I'll not get into bilevel programming as such because this is known, a lot of these stories have been told. I'll just go to this problem. This is exactly the problem I have been telling about. See what happens when you take the upper level function f and the lower level function g, both differentiable or smooth, whatever you want. Of course, we are having convex data. Without convex data, this lower level problem wouldn't have much meaning because nobody wants to solve a hard global optimization problem. See, the problem is that whenever you take f and g to be smooth, to have a good convergence analysis, an important assumption is that the gradient of both f and g is Lipschitz. So that's a very important assumption. But if you look at the book of Amir Beg, first order conditions in first order methods for optimization, then you will see that the examples that he gives for such class of functions is very specific, and you are always not sure whether given the problem you have such kind of functions. So our question is that can we develop an algorithm for this class of problems where we do not take the Lipschitz gradient assumption? That's the thing. And then compare it numerically with those algorithms, at least one, which has such issues, which takes Lipschitz gradient as an assumption. See, so here again, just to mention the problem here, f is convex and g is convex, c is a convex set. C can be described by constants. That's just additional detail. Let me just see that what kind of problems we might come up with when we are trying to find a model for this particular set of problems. One of the problems is that of compress sensing. In compress sensing, what happens? You are asked to find a sparse solution of Ax equal to B. What might happen is that this matrix might be ill-posed and you might not be able to find so easily a solution of Ax equal to B. But you might be just happy, even in the situation of compress sensing, to have a least square solution. But that least square solution, you at the same time, you want to have a least norm. So then you pose it in this particular form of the simple bilevel programming problem. Now, and so this is a problem of compress sensing, which we have posed in this problem. And we have actually got, I will show you a numerical result at the end where it shows that it actually solves it pretty fast, this approach. Okay. Now, trying to solve this problem, we have not tried to solve this separately, but putting it in this actually solves the problem pretty fast. Okay. Now, this is one example. Another example which has been of a great interest to me for a long time now is that I have seen a lot of papers on error bounds. In fact, my last paper was also on error bound. So in error bounds, we have known for long error bounds of convex inequality systems. But once you want to get an error bound, which is of a global nature, you need to assume Slater condition or sometimes largely not Slater, more stronger than that, called strong Slater's condition to get an error bound. But my interest has always been that when you solve a convex optimization problem and you stop with some xk, iterate, how good is your iterate? One of the ways is to see how far it is from the actual solution set. And as a result, that is best given by error bound. So error bounds are very good stopping criteria and also used in convergence of algorithms. So given a convex optimization problem, can I find an error bound? If I take a convex optimization problem, we'll immediately see I can write the argmin set as a system of inequalities and system of convex inequalities. But the problem is that the Slater condition will immediately fail in that. And as a result, we cannot apply the standard known error bound for inequality systems to that set. And so it becomes very difficult to find an error bound. In fact, I tried this even with John Borwein with having some very strong conditions. We could do something, but not much. But if I'm talking about strong convexity, there is this whole theory of gap functions which comes to the rescue. But if I have a convex function which is not strongly convex, which that wouldn't help. Even if I am talking about linear programming problem, I need to know the infimum of the problem in order to apply the Hoffman error bound to get certain things. So now I thought that, okay, if I cannot get it algebraically or analytically for a convex problem, can I at least get it numerically? So if you give me an xk as your approximate solution, can I numerically tell you how far it is from the solution set? So that gives rise to this kind of problem. So here you are solving this convex optimization problem. This is your core problem. And then you are basically, so this is the core problem. And now you want to find the distance of your, for any x in C, you are trying to find the distance from the solution set. So you have chosen kind of some x, which is your solution. And then you want to find, when you say that it is a solution, you want to find what is the distance from C. So it can be even C could be Rn, doesn't matter. Then basically you are solving this simple projection problem, but where S is equal to this. Please understand how my core problem is this problem. So if I solve this problem, so now it's a bilevel problem. So what I'll do, the idea is not really to solve the core problem, but actually immediately give you, once you give me an X, I'll immediately give you this distance. So without really going into the solution of the core problem itself, because there could be infinite solutions, then you can't do, you can never really see the whole solution set. That is really not possible. So let's get into our steps. The approach in bilevel programming, whether it is taking two level with two variables or just one variable, has always been to convert it into a single level optimization problem. So the idea is that usually what you do for the usual problem is to write it as this type of problem. So minimize fx, gx less than, as for example, if I say alpha is the infimum and x element of c, you write the lower level objective itself in the constraint. Now the interesting fact is that once you do that, there has been several papers which says that this kind of formulation won't work for this problem. There is a paper by Beck and Shabak, which in math programming, which says that no, this kind of problem, you can't handle this by doing this type of formulation. What we decided that, okay, we take a alpha k's which are bigger than the infimum. Suppose we can do that. We can take an alpha k bigger than the infimum. And then for each of them, what would happen if I take alpha here? This is a bad situation in ill pose because Slater condition fails if I take this to be the infimum. But if I take something much bigger than the infimum, my Slater condition holds, and as a result, I can apply standard algorithms. So can I construct those alpha k's? I do not know what is the infimum of the lower level problem. Still, I should be able to successfully construct the alpha k's which are bigger than the alphas. And then I successfully decrease the alpha k's and solve a sequence of problems and get to the solution. That's the key idea. So we'll see how we do it. So you see, if alpha k is a real sequence of real numbers which are strictly greater than the solution of the lower level problem, and suppose the limit of alpha k goes towards the minimum of g, the minimum, the infimum value, then if each problem, if you solve all of these, each of these problems have a solution xk, then this xk will converge to the actual solution of the actual problem. So what we have there have been some suggestions like, why don't you, okay, you say that this is a bad problem because if alpha is the infimum, then this Slater is not satisfied, so it's bad. So why don't you, instead of trying to solve the lower level problem, try to solve the a kind of get an approximate solution of the lower level problem and then try to do something. But for this example, which I will not discuss in too much detail, what we show that if we, for example, we take a very simple upper level problem is quadratic, strongly convex. Obviously, most cases you have a strongly convex function to choose just one solution among many. So what happens that if you take a if you take a lower level problem in this way, and if you choose an approximate solution, you want to choose approximate solution, that is, you want to solve something like this, then the solution of this problem may not give me a solution of this problem. So just by choosing an approximate solution of or an epsilon solution of a lower level problem does not do any help for me in actually solving the original problem. So this is an example which shows that. So here is an algorithm of the problem. So let us discuss this algorithm. First of all, we will have an assumption that our function f will have no assumption on it, no differentiability assumption. We will have an assumption of differentiability on the lower level problem. The lower level function g, lower level convex function g will be assumed differentiable. But we will not go and make any additional check whether it is having Lipschitz gradient. We do not make any assumption of Lipschitz gradient. This idea was taken, we were trying very hard and we were not able to get through anything. But suddenly we get a paper of Alfredo Usem in some conference proceeding. It is just on searching the net. And then we got a kind of Armizo kind of backtracking rule like this. And that suddenly helped us. But it was very, we were just been very lucky. Just I cannot say that I had completely understood the problem and we got into it. We were just lucky. We said, okay, let us take out this rule and let us put it for this case and let us see what happens. And it worked. And it worked beautifully numerically. And that is why optimization sometimes becomes an art more than a science. So here are certain standard things. You fix up certain control parameters. Of course, projection becomes a very important thing. Please understand, when he soloed out did his problem, what he did, he had the f on the top, he had the g in the bottom. So he constructed a function of the form g plus epsilon f, a penalized version of the problem, and minimized it by a projection method, the projected gradient method, over the set C. That was his approach. So we will take a projection, but only projection using the lower level function. We will not do any kind of penalization. You see, our attempt is very simple. We are just trying to first try to see whether we can get some idea of a solution of the lower level, and then we think of the upper level, right? So what we do, there is a result where we can prove that if we have a condition like this, then g of xk is the minimum of C. And if we do not have this condition, then we try out this backtracking search. Now, once we do, you see there is a two-step thing here. We are doing a two-step thing. First, we are finding a yk, which is computed out in this fashion. Zk comes here. Zk is, you see, let us look at the steps. Step 3, we are taking the xk, kth step, and then doing a projection step and getting a zk, and then making a check of this quantity. Suppose if this is less than 0, we find a backtracking search step length, and then we put that step length as 2 to the power this whatever we get here. This is a USEM step length, and then you get this. You do this updating with zk, the projection point. This is the updating for the lower level, and then you set alpha k is g of yk. Once you do it, okay, there is a lot of story behind it. There's a lot of theory behind it, for which I don't have time at this moment, because I'm more keen to show you the numerical part. Then you solve a problem like this. You can actually construct the eta k in such a way so that alpha k plus eta k is always bigger than your infimum. That there is a proof in our paper, right? We are not sending it, we'll be just sending out that paper. So here is a two-step thing. So now xk plus 1 is now the solution of a problem like this. For this problem, which has a Slater, where Slater condition is satisfied, because this is strictly bigger than the infimum, we can now apply any standard algorithm. We have, in this case, we have used what is that called, CVXOpt, which is a part of the Stephen Boyd's algorithm, which is a part of MATLAB. So here is a kind of black box type of approach we have taken here. Okay, so let us see what is the math behind it, what it says. So what it ultimately says is that if we are constructing or using this algorithm, the sequence that we get, if we, for every xk, if we compute the distance from the actual solution set, then this distance is actually going to 0. This is the standard in bilevel programming. When you have this problem, you're not really showing xk going to some x star, but you're showing that your distance from S is actually coming down, right? So in some sense, it is actually converging to some boundary point, and hence a solution. Now, this set C that you need in the lower level in this particular scenario needs to be compact, because we also need that the lower level problem actually has a solution. So there will be interesting to see how can we remove this compactness. We haven't been able to do it yet, but maybe that would be a very good problem to work on. So here is some stopping criteria. There can be many ways to stop the algorithm. See, when we are writing an algorithm, we are not writing a stopping criteria, but it's very important to say that when you want to implement the algorithm, what should be your stopping criteria. So our stopping criteria is largely based on this, that, you know, this alpha k, which is essentially trying to generalize, which is some quantity higher than the infimum value. If their difference is becoming very less, but that is, they are giving some Cauchy sequence type behavior, which means they're converging to the infimum, we can stop. And at the same time, this difference is also less. that the functional value, this difference between fxk and fxk minus 1 is less, we will stop. So that is a kind of stopping criteria we decided. And then we wanted to see what happens with the algorithm. So let us look at this problem. Okay, the upper problem is a kind of is a linear affine function. And this is the convex function which we will be taking at the lower level problem with a compact set C. This is my C. This G, the gradient of this function would actually have, of course, F is having Lipschitz gradient. These are both having Lipschitz continuous. What we are doing is, in this particular case, we are trying to compare our algorithm with Solodov's algorithm. And what we are observing is that we are very fast in a standard Lenovo or standard PC. And you will see the iteration number and the CPU time. So this particular choice of eta k is for our algorithm. And this is the step length. This is the epsilon, the threshold that we have fixed up. So the solution is almost same for both the algorithms. Solution doesn't differ much in both our algorithms. So you see our algorithm is throwing the same solution for if this eta k, this particular control. You see, look at the difference between the iteration number of this and Solodov's algorithm. And look at the CPU time in seconds. So our algorithm is a huge improvement even for the case where we have Lipschitz gradient. So what we did, we instead of Lipschitz gradient, by luck, we used the USEM's criteria, USEM type backtracking search. So that is a very lucky thing, actually. This is sheer luck. I can't say that I really figured it out. It was just sheer luck that I decided to pick that up. Somehow I think that it would work. Look at what happens. You see look at what happens when we are trying to make the threshold much more tighter. You are getting, you see, my algorithm is throwing up similar kind of same solution. Solodov is also throwing up similar solutions. But look at the iteration count and look at the CPU time. In fact, when I'm making the thing much more tighter, Solodov doesn't seem to even give me anything even after 10,000 iterations. Well, we are stopping at 28 iterations. Solodov's algorithm, it worked for 16 hours actually. This is just a figure we have given that, okay, we'll assume that we have stopped after 10,000. After 16 hours, it didn't give us anything. I had no idea why. So here is a linear system. It's very simple toy example for compressed sensing. I do not say that my example will actually work for real large scale problem, but for a simple small case toy problem, it is working. The issue with simple bilevel programming is that there is no library of test problems on which you can actually do the checking. So this subject is actually, it's a new thing which is growing up. And so there are a few researchers who are working on this kind of problems. And so possibly a set of test problems would gradually come up in the after some years. So here is a thing for which we can have a solution. Of course, it has more than one solution. You have 3 equations and 4 unknowns. So here we put it in this setup, and you see that we are getting pretty fast. We are getting our optimal value, and in fact, you see the solution is sparse. Even for whatever be the threshold, of course, there is a rounding off here, numerical rounding off. This is not really -1, it is some point something, but of course it gets rounded off. So this is out of 4, 3 are empty. So it's giving me a very good sparse solution. But again, I would admit, and I'm written that in the paper, is that I cannot guarantee anything what would happen in the real large scale scenario, whether this will work or not. But for this simple scenario, at this moment, I'm seeing it is doing a pretty good job and pretty fast. So now comes one of my thing which I have been working, which I like very much, is estimating the distance of the solution set. So in this case, again, so So the lower level problem is non-different. Hello, the function f is non-differentiable. And you see here f is non-differentiable because we take a max function. And then the function. So here we are trying to get the distance from the original set. So when we are using our approach, right, then actually you don't have to, if you write it up, this problem would actually turn out to be, though it's looking like this, this will actually turn out to be differentiable. So here also, with the certain threshold, you can actually get the distance. Sometimes these ones are all rounding off. Okay, you can see this is what's throwing out. But in a very less number of iteration, you can know whether your chosen solution point, how far is it from the solution, how far it is from the solution set. This distance is being given. So this is at least this algorithm for the time being seems to work well. And please understand that there is no assumption of any Lipschitz gradient. We are not assuming, for example, this problem, for example, does not have a Lipschitz gradient. So this is working even without any assumption of Lipschitz gradient. So I guess with this, I will stop my talk, and I hope there will be comments. Thank you.
Can I ask a question?
Sure, Regina.
So thank you very much, Joydeep, for very nice talk. I think I learned a lot from this talk. Look, the lower level set, you said that you wanted to get rid of the compactness assumption.
Yes, yes.
I wonder if you could introduce some coercive regularization or in the lower level function G by summing up a multiple of a coercive function, a multiple that goes to 0 when k goes to infinity. In that way, you will ensure that you always have a solution of the lower level.
Okay, right. That could be a good idea.
You know, if you show me the algorithm, I can be more precise.
Yeah.
So in the moment, so you said that you wanted to ensure the solution in the step 5, right?
Yeah. In
so
the
where do you want to?
I want to ensure that in the step 5 also I should have a solution. Yeah. Actually, the lower level should have guaranteed have a solution. So then I can work with it. But I'm sure.
So
basically.
the moment in which you need that is in step 5, right?
Yes.
So you could either place a regularization here in G instead of using G, or in the objective minimization of f plus some epsilon k times some coercive function, and that multiple of the coercive function goes to 0 when the process when k tends to infinity. So in that way, you don't need to ensure compactness of C, and you will always have a solution, a unique solution actually of the.
Yeah. For this, every problem would have a unique solution, and finally it will go into the right. Finally, this will go to the solution. Yeah. That could be done. Yes.
Because for general choices of F and G, you may not have a unique solution in the step 5.
No, I know there's no guarantee I'll have a unique solution. Yeah, that way I'll have a unique solution, which is a very good idea. It's a very good idea. Okay. So this is a very good suggestion. Maybe we'll do some improvement on the paper. Thank you very much, Regina.
No, you're welcome. I hope it works.
Yeah. I have not seen you for a long time now anyway. So I hope we'll see each other after the COVID goes off. It's a very funny
Okay.
money. I have now money to travel and I cannot travel.
Are there, sorry about disappearing there. My internet dropped out for a second. Are there other questions for the speaker? Well, if there are any other questions, if anybody thinks of any, remember that we also have the Slack that we can participate on and ask questions on.